Hi everyone, my name is Omkar and I will be presenting on Lyapunov-based hierarchical trajectory control of an autonomous ground vehicle subjected to slip. I am from University of Florida and my co-author Dr. Shubhendu is from IIT Delhi. To motivate this paper, let's talk about autonomous vehicles. So, autonomous vehicles have received a significant amount of attention from researchers in the previous decade, as we have seen. And control design is an important aspect, which mainly involves addressing the trajectory tracking or the path tracking problems. Before designing a controller for any system, we need to know the underlying dynamics, or at least the nature of underlying dynamics of the system. So for autonomous vehicles, the traction forces which drive the vehicle are generated by the underlying higher order longitudinal and lateral slip dynamics. These two dynamics are non-linearly coupled, which makes the control design procedure challenging. To address this problem, researchers have often treated the longitudinal and lateral subsystems as separate decoupled systems. However, it's a restrictive assumption and that often requires restrictive conditions on the states. Therefore, nonlinear coupling between the slip dynamics needs to be considered while designing our controllers. So there are MPC-based techniques which address the trajectory tracking problem in presence of coupled longitudinal and lateral slip dynamics. However, the Lyapunov-based techniques are not explored very well. And this is because there is a main challenge that involves the unique nonlinear and coupled switch nature of the combined dynamics. And this structure of dynamics makes the backstepping approach difficult to directly apply. So in this presentation, I will demonstrate a nonlinear hierarchical control design to address the trajectory tracking problem in presence of the coupled slip dynamics. In order to derive the combined vehicle dynamics, which would facilitate the control design procedure, the vehicle body dynamics are first evaluated using Newtonian equations of motion, and then we'll subsequently derive the wheel slip dynamics and combine them to get the dynamics which we need. So the vehicle body dynamics are derived from the Newtonian equations of motion as shown. Now let's look at how a wheel generates its traction forces. So the traction force generated by the wheel has longitudinal and lateral components. The longitudinal component depends on a quantity called slip ratio, which is defined as the ratio of slip velocity over r omega, or the longitudinal velocity of the wheel, whichever is greater. Similarly, the lateral force generated by wheel depends on a quantity called slip angle, which is the arctangent of lateral component of wheel velocity over the longitudinal component, as shown in the diagram. Substituting the tire model into the vehicle body dynamics, we get the combined vehicle dynamics represented by these four equations. Now here, our control inputs are the motor torque T and the steering angle delta. The design procedure would involve a nonlinear hierarchical control design where the slip ratio lambda and the side slip angle beta are treated as virtual control inputs. So the actual control inputs T and delta are designed to track the virtual control inputs lambda and beta, which are designed according to the subsequent Lyapunov analysis. It may be observed here that the dynamics are not in a strict feedback form and they are non-linearly coupled, which makes traditional backstepping design difficult to apply. However, a nonlinear hierarchical control design is certainly possible by Lyapunov based design, which I will demonstrate. So I'll explain the hierarchical control design procedure using the block diagram shown here. So first we have a reference model which generates the state QR based on the reference velocity and the reference angular velocity inputs. And then we get the reference value of QR based on this reference model. So QR would consist of the reference value of x coordinate, the reference y coordinate, and the reference orientation angle theta. So our control objective is that the state Q should track QR. So we have Q in the feedback loop shown here, and so accordingly we get the tracking error EQ, which is then fed into the kinematic controller. The auxiliary velocity or kinematic control inputs are then designed as shown in this equation. This design is based on subsequent Lyapunov analysis, where Vc is the virtual linear control input and theta c dot is the virtual angular velocity control input. So theta c dot is fed into the angular velocity controller as shown, and Vc is fed into the inner loop. So here we have a feedback of the velocity V, which generates the error E4. Then the next step is to track our virtual angular velocity input, which gets perfectly tracked by designing the steering angle delta as shown in this equation, where the expression of uay, an auxiliary variable, is outlined in this equation. These expressions are designed so as to cancel the remaining terms in the dynamics, which would facilitate our subsequent Lyapunov analysis. Similarly, the next step of hierarchical design is to track the virtual linear velocity input Vc. In order to track Vc, we temporarily assume that our acceleration can be treated as a control input to track Vc. So accordingly, the desired acceleration AR is designed as shown. And based on this value of AR, we design the corresponding value of desired slip ratio, that is lambda d. So the output of the linear velocity controller is lambda d. The next step is to track the desired or the virtual slip ratio lambda d. So accordingly, the control input torque T has to be designed. In order to design this, let's first look at the dynamics lambda dot. So the dynamics in lambda dot are a switch system because lambda was defined differently for each of the two cases. So here we have our control input T in both the expressions. But here we can design T for each case such that the rest of the terms get cancelled, and then we have the same expression for lambda dot for each case. So T has to be designed accordingly, where this term U lambda dot showing up in these expressions is designed as shown in this equation. This term is designed according to the subsequent Lyapunov analysis. Substituting the controller expressions into the vehicle dynamics, one can obtain the closed loop error dynamics. Now for the stability analysis, the candidate Lyapunov function is selected as V, which comprises of E1 square, E2 square, E4 square, and E5 square base terms, and also a 1 minus cos E3 base term. It is justified to use this term because E3 is an angular orientation error, Taking the time derivative of Lyapunov function and substituting the closed loop aerodynamics yields the expression for V dot as shown. This expression is negative semi-definite because cos beta is positive. And cos beta is positive because beta always lies between minus pi by 2 to pi by 2. And then by some signal chasing and invoking Barblett's lemma, it can be proved that the errors asymptotically converge to zero. So based on the nonlinear hierarchical controller design, as I explained, the simulations are performed considering an electric race car used for Formula Student competitions. A hyperbolic tangent shaped lane change trajectory is considered as shown. As one can observe from these plots, the convergence of the trajectory to the desired trajectory is observed. Similarly, one can observe that the longitudinal tracking error E1 converges to 0. Similarly, one can observe that the lateral tracking error E2 and the angular tracking error E3 converge to 0 asymptotically. The torque and the steering angle control efforts, as shown, are within the permissible range for the electric vehicle. Though there is one problem here, that the steering rate is slightly high initially. This is probably due to some inherent non-linearities which get cancelled in the design procedure. So future work has to be directed to address this problem. So to conclude, a nonlinear hierarchical trajectory tracking controller is proposed, and the stability is guaranteed using Lyapunov-based analysis, and simulation results demonstrate the asymptotic convergence of the closed loop error system. Now, this controller is applicable only when slip ratios and slip angles lie in a bounded region, because only in that region they have a linear relationship with the traction forces. However, when the slip ratios and the slip angles get outside the bounded region, the linear relationship is no longer applicable. So future work has to be directed to constrain the slip ratios and the slip angles to the desired region. And it is also important to ensure the robustness of the closed loop error system to parametric uncertainty. Thank you.